Hey guys, how's it going? Today's lesson is on buffers, and buffers resist changes in pH. That's what buffers do. So for example, your blood is pretty neutral. It has like a pH of 7.6. Like it's pretty neutral, right? Some is pH 8. You can see it's leaning towards slightly basic because it's greater than 7. But how do we make sure that our blood pH stays around like neutral? How do we make sure that happens, right? Because what happens if our blood becomes too acidic, right? And like it gets like to be 6, right? Well, we won't be able to function, right? We function at an optimal temperature of 7.6. So buffers in our body help to resist changes in pH. And an example of a buffer in our body is the blood buffering system. Okay? And this blood buffering system depends on a weak acid. Okay, so weak acids are extremely important when you buffer blood. The thing is when you have a strong acid and you react it with a strong base, like that, the reaction is going to be intense. What is this thing? The reaction is going to be intense, okay? The strong acid is going to have all this H positive that it's coming off of it, and the strong base is going to like grab all these H positives like super quick, and you're going to get this like really strong reaction. So like whenever you spill a strong acid, you actually want to neutralize it with a weak base. Now, why is that? Why is it if you spill a strong acid, you want to neutralize it with a weak base? Well, again, if you're a strong acid like HCl, you're going to be losing all these H positive ions, right? Because the strength of an acid, it depends on how, the strength of the acid depends on how easy it is for H positive to be released, right? The stronger the acid, the more H positive you make, right? Well, if you have a strong acid and you spill it, why do you want to neutralize it with a weak base? Because the weak base will actually grab onto the H positive more slowly, so the reaction is not going to be as intense. So the weak base will like grab onto the H positive more slowly than a strong base would. So here we go, one at a time. It's grabbing hold of these H positives. And so you're going to get way less of a reaction occurring when you neutralize a strong acid with a weak base. And the same thing happens when you have a strong base. What do strong bases do? If you spill a strong base, right, these tend to grab H positive, right? They just grab onto it really like a lot. So you want to neutralize it with a weak acid because the weak acid tends to hang on to their hydrogen, right? So weak acids produce less H positive, right? And because they produce less H positive, then it won't grab it like as much. It will grab it with less force, and the reaction is not going to be as intense, right? So if you spill a strong acid, you neutralize it with a weak base, okay? Because if you spill a strong acid and you neutralize it with a strong base, the reaction is going to be explosive, right? You want the weak base to neutralize the strong acid slowly. Just like if you spill a strong base, you want the weak acid, right? So the H2SCO3 produces less H positive, right? When you have less H positive, this will grab the H positive like slowly, and the reaction will be less intense, okay? So that's why you neutralize strong acids with weak bases and strong bases with weak acids. Okay, your blood buffering system relies on weak acid, and it relies on the weak acid H2CO3. Okay, now the H2CO3, right, can disassociate, right, to form H positive and CO3 to negative. HCO3, sorry. This is HCO3, so we're going to, H2CO3 can disassociate to form HCO3 negative plus H positive, right? And remember, it's going to produce less H positive, right? Because it produces less H positive, so remember H2CO3 is in your blood. It's part of your blood buffering system, right? Remember, a buffer resists changes in pH. Now, how does your blood do that? So here you can imagine like, okay, well, let's just draw this, okay? Imagine that this is your blood, right here. Do do do. Do, 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 do. And inside your blood, so here's your blood. Inside your blood is this hydrogen carbonate, right? Which is a weak acid. It's a weak acid. You can even check your data book, and it will show you that it is. I can't find my data book, but you can check your own. Anyway, so here's your blood. Inside your blood is this. It's producing this, okay? This is bicarbonate, okay? And this is actually pretty basic. Okay, so this is what's making your blood kind of more basic. And because it's a weak acids tend to hang on to their hydrogens, right? So because they tend to hang on to their hydrogens, right? They don't want to let the hydrogen go. You're going to make H positive, but you're not going to make very much H positive, right? You're going to make less H positive. And so what happens is if you drink like, I don't know, Coca-Cola, right? Like not cocaine, but if you drink Coca-Cola, right? Well, Coca-Cola has a lot, it's acidic, right? So what ends up happening is you start making all this extra H positive from drinking this Coca-Cola, from eating the orange, and all of a sudden you're adding H positive to your blood, right? Because you drank this. Well, you don't want your blood to become too acidic. Remember what I said before? If your blood becomes too acidic, your cells don't function properly. So you want your blood to stay pretty basic. So how do you do that? Well, when you drink Coca-Cola or you eat an orange or you do anything like that and you add H positive to your blood, hey, guess what? This bicarbonate ion will actually, right, start to hang on to the H positive, and it will make the reaction go that way, and you're going to start producing more of these, right? So the H positive, right? The H positive is actually taken up by the HCO3 negative, right? And because it's taken up by the HCO3 negative, you're going to see, right? If you have H positive plus HCO3 negative, you're going to start making more H2CO3. And in this way, this bicarbonate is actually buffering your blood, right? It's actually removing H positive so your blood doesn't become too acidic. So this here is resisting the change in pH. And that's how buffers work, okay? Now, I hope that helps. That's all you need to know about buffers. Buffers resist changes in pH. In your blood, this bicarbonate ion is what's resisting the change in pH. If we add hydrogen to your blood, it will accept the hydrogen and the reaction will go this way. And you start producing more of this, okay? And that is buffering. Now, you guys, you're going to maybe see a chart on buffering, and you guys can see, like, if this is the chart and here's your pH, here's buffering, right? You're going to be buffering your blood until eventually, right, either it's going to go this way or it's going to go this way, right? So that is how a buffer works. So this is the part here that's resisting the change in pH, okay? And then eventually, though, like, let's say, why is this happening where it becomes so basic or so acidic? It's because when you have all these hydrogen carbonate ions, right? Like, so remember the reaction that I just showed you where you have H2CO3, that makes HCO3 negative plus H positive, and that this acts as the buffer? Well, hey, what happens if there's like way too much H positive? Like, it's like overwhelming how many H positives there are. Oh no, oh no, oh no. Well, this can only accept so many H positives and draw it back that way, right? But if there's way too many H positives and it can't attach to all of them, then you're going to see this real change. The buffer can only buffer for like a certain amount of time until eventually it cannot anymore because there's just too many H positives, and then this starts to happen. And you don't want that to happen because it could be bad for your health, right? Anyways, that is on this page 33 of your booklet, this blood buffering thing. There's a little bit about it, and I did a little bit more on it. And then the next lesson is going to be on environmental chemistry, okay? Okay, take care, bye.